So that's like the next plan. Save up money, hire a year. Start a perpetual cycle of that.
I always wanted to do that. I only have one next to Kristen. But my wife is always like, just wait till you graduate.
Yeah, that's what I'm
probably
saying.
right.
I'd say,
To have money to.
yeah, it's a bit like that. Mhm.
It's fun.
It's good training, I like it.
Are you ready for that? Okay, we will do the exam on 15. Yeah,
James.
Tuesdays.
It's Wednesday, right?
So Wednesday.
The 15th would be Wednesday.
Is it Wednesday?
Yeah, it is.
Yeah, it's actually Wednesday.
Are you gonna be in the tutor center tomorrow?
Oh, yeah, you want to come over?
Yeah.
Okay.
I went last test, the day before, but you weren't there.
Ah, really? You could have just told me because there is no one who comes there. And...
I'll probably-
If no one shows up,
I'll
you
go
leave.
tomorrow. I'll go tomorrow, probably like 10:30-ish.
Okay, just let me know when before you come because I just leave around.
Do you want me to just send you an email?
Just send me an email. Yeah. Yeah, I went there for like 3 times. No one is coming. I was like, why am I wasting my time?
Yeah.
Yeah. So I'm always, most of the time I'm in this, what is the name of this restaurant? College Market?
Yeah.
Yeah, I usually sit there. So if you want to come, we can actually meet there.
At the college market?
Mhm.
Okay.
That's just off campus on like
That is very
12th Street or something, or 10th Street.
Yeah, it's actually along this,
My bike.
which avenue is this? Is it 8th
I gotta
Avenue?
run
It might be 8.
Yeah, just down there, just
Yeah.
1 minute to 2 minutes.
Yeah, what is there? Is it just like small grocery store? or a
No,
cafe
it's
or-
something like a restaurant,
Okay.
so you can actually have your breakfast there.
Sure.
Get some food there.
Oh, man.
Nice.
Mhm.
I ride my bike
Not
all
the
the
one I
time.
normally ride.
Mhm.
It looks cool.
Yeah.
There's a lot of places I haven't checked out here in Pocatello yet, but
Mhm.
just went to Goodies for the first time yesterday. It's delicious.
It's great,
I
right?
like it a lot.
I haven't
Do you
been
eat
there,
the
but I
bun?
want to.
No, I just got a sandwich. Yeah.
Their calzones are great. I think it's Tuesday is their special.
Nice.
Yeah, I mean, it's huge. too.
Where is that?
The pizza bombs,
Where is it?
it's a calzone. It's like a pizza and then they fold it in half.
Oh,
So it's crust on.
which
It's
restaurant is
Goodies.
It's like Goodies right
Goodies?
across the street,
Oh, oh.
next to Elmer's.
I wanted to, but I have to wait.
It's good.
I usually prefer Five Guys for the.
Five Guys is a
Five Guys.
good burger, man.
Yeah.
I like Five Guys.
Yeah,
Can't argue with that.
I like Fifth Street Bagelry sandwiches a lot. I just want to say,
Sandwiches are good.
yeah, breakfast sandwiches or the California Club.
A lot of good
Pilgrim.
food here. A lot of good food.
There is, and there's a lot of good Mexican food.
Mhm.
Okay, let's continue. Let's do an example on what we were doing last time. It's example number 2. So compute each determinant if determinant of A, B, C, D, E, F, G, H, I is equals to 2. Is equals to 2. So number A. A, B, C, D, E, F, minus 3G, minus 3H, minus 3I. So what is the determinant now? So you remember the last statement we wrote. When you have K inside, KAI1, KAI2, like that. Then what do? You factor out what? You factor out K, and in this case, you factor out -3 there. So this is actually similar to -3. The determinant of A, B, C, D, E, F, G, H, I. And we know this one is what? This is 2, right? So it will now be equals to -3 multiplied by 2. And this is equals to -6. So the determinant there is -6. B. Find the determinant of G, H, I, D, E, F, then A, B, C. What happens here? We are switching, right? So we are switching this. So when we switch, what happens? When you switch, then it becomes negative, right? So this is actually the same as negative A, B, C, D, A, B, C, D, E, F, G, H, I. So in this case, this is equals to negative what? Number C. Find the determinant of A, B, C, D minus A, E minus B, F minus C, G, H, I. What was happening when we add or subtract the constant by a constant? Determinant does not change, right? So it doesn't change. So the determinant is actually 2. So these are following the elementary row operations. So when we multiply by this constant here, then you can actually factor out the constant and then find the determinant. So it's like this. When you switch the rows, then the determinant becomes negative. When you add the constant, the determinant does not change. So it does not change. Okay. Example number 3. Number 3. So this one, remember, I'll give you this one in your third exam. This will be in your third exam. Something like similar to that. Example number 3. Compute determinant of 1, 3, 3 minus 4, 0, 1, 2 minus 5, 2, 5, 4 minus 4, and then minus 3, minus 7, minus 4, and 2. Minus 4 and 2. So we can actually get a determinant here by reducing this to echelon form, whereby we can make this to be a triangular match, whereby the below the main diagonal there are 0 entries. So we can reduce this. So we can reduce this one, that, and that one to be all zeros. To be all zeros. So in this case, then we can get the new R3 to now be R3 minus 2R2, my I2R1, and then the new R4 to be R4 plus 3R1 plus 3R1. So what you get there is 1, 3, 3, minus 4, then 0, 1, 2, minus 5, and then here you get 0, minus 1, minus 2, 4, then 0, 2, 5, and minus 10. Also, we can make this one to be 0. And then also we can make this to be 0. So actually it is now like that. So to get the new R3, then R3 plus R2 to get a new R3, R4, then R4 plus or minus 2 R2, minus 2 R2. So 1, 3, 3 minus 4, 0, 1, 2, and then minus 5, then 0, 0, 0, minus 1, and then 0, 0, 1, and then 0 here. So that is what you get then. Okay, I'm doing it wrongly here. This is actually, put this one. This is actually determinant here. Determinant here. So it's actually determinant. Now, looking at this now, since we want to make this to be the diagram, instead of continuing to reduce this, what can we do here? Okay, let's switch. Now, when we switch, what happens?
If the term becomes negative.
Negative, yes. So here now, when we switch here, so we can switch R3 and what? R4. We can switch R3 and 4. And then it will now be negative, determinant of 1, 3, 3, negative 4, 0, 1, 2, negative 5, and then 0, 0, 1, 0, 0, 0, 0, negative 1. And finally, this will be equals to what? Negative 1 multiplied by 1 multiplied by 1, negative 1. And this is equals to what? 1. Equals to 1. Any question up to that? Okay. Another example where we can combine the row reduction and the core factors method.
I've got a quick question before we move on. When you switch the rows, the determinant is multiplied by -1.
Mhm.
But if you, for some reason, maybe there's a matrix where you have to switch rows twice, is that then maybe -1 times -1 times?
Yes, yes.
Oh, so every time. you
As
switch a
long
row-
as you switch,
Okay.
then determinant become negative.
So
When you continue switching, also negative.
multiply by another -1.
Yep.
Okay.
Mhm.
Gotcha. So that just continues going.
Yep.
All right.
Okay, example number 4. Combine the row reduction and core factor expansion to compute determinant of -1, 2, 3, 0, 3, 4, 3, 0, 5, 4, 6, 6, and then 4, 2, 4, 3, 4, 2, 4, 3. Okay, so we can combine the row reduction. Okay. If you look at the last row here, the last column here. So since we use the row or the column returns as many zeros as possible, and in this case, we can make this one to be one. So we can make this. So how can we make that to be 0? So in this case, we want to get the new R3, whereby this new R3 will be R3 minus 2R4 minus 2R4. So in that case, then what we get is -1, 2, 3, 0, 3, 4, 3, 0, and then here will give you what? -3, 0, -2, 0, and then the last one is 4, 2, 4, and then 3. And then we do what? We use the cofactors. We now use the cofactors. Taking now this one. Then it will now be 3. So it will now be 3 multiplied by -1 raised to what? 4 plus 4, right? 4 plus 4. And then determinant of -1, 2, 3, 3, 4, 3, and then -3, 0, -2. Okay, are we together up to that? We close this and this one. Now, looking at that, we can also make this one zero. Since we have 0 here, we can do what? We can make this one by reducing. So what can we do there to make that to be 0? So basically, this case, this is just the same as 3, right? 3 here, because 4 plus 4 is 8. -1 raised to 8 is what? 1. And then, so basically, what we can do is we can make this one to be 0. To make this one to be 0, then what we are looking for, we are looking for new R2, which will be what? R2 minus 2R1 minus 2R1. So in this case, 3 is outside. 3 is outside, which is this 3 here. So here will be -1, 2, 3, and then this will be 5, 0, -3, and then -3, 0, and -2 there. Okay. And then finally, since this has as many zeros as possible, then this is the same as 3 multiplied by what? 2 multiplied by -1 raised to what? 1 plus 2. And then determinant of what? 5, -3, -3, and -2. And finally, this is negative, right? So this is -6 multiplied by -10. -10 minus what? -9. And this is equals to -6 multiplied by -19. And this is the same as what? 114. So that is how we can use the reduction and go forward. Remark. this remark, you will get it in your exam as a question. If A is an n by n matrix, and K is a scalar, then determinant of Ka is equals to K raised to n, K raised to n, determinant of A. If it is a 3 by 3, if it is a 3 by 3 matrix, then if you given here determinant of K A, then it is the same as K raised to 3. It is a 4 by 4, K raised to 4. 4, 5 by 5, K raised to 5. Okay, properties of determinants. Of determinants. Properties of determinants. Okay, the first one is actually what we just know, that an n by n matrix A is invertible if and only if determinant of A is not what equals to 0. So that is a first property. As long as the determinant is not equals to 0, then it is invertible. So we have seen a lot of examples on that. So you just need to get the determinant. And if it is not equals to 0, then it is invertible. If it is 0, then it is what? Singular. It is singular. Property number 2.2. We can take this one as a theorem actually. V1, V2, all the way to Vn are elements of the vector space, which we can take this as Rn. Are linearly independent if and only if determinant of now putting this one as a matrix V1, V2, all the way to Vn is not equals to what? Equals to not equal. So actually using the properties of linear vectors, linearly independent and dependent. So if you find that it has 0 vector, then definitely that is not what linearly independent. So in that case, if you put them in a matrix form and then you get a determinant and the determinant is not equals to 0, then that means all those vectors there are linearly independent. Another property, an example is just the same as removing the columns and put them as a vector, the next column like that, and then when you combine them, and you find the determinant is not equals to 0, then they are linearly independent. 2.3. Before 2.3, let's do an example here, which will lead us to 2.3. Example. You want an example one? Example 4, example 5. Let B to be equals to 1, -1, -3, 1, 1, -5, 2 minus 2, -5. Yeah. Then find determinant of B and determinant of B transpose. And I think we solved this, right? You still remember? I still remember doing determinant of A and determinant of A transpose. And they were what? They were the same. So basically, when you get the determinant here, so determinant of B is equals to 2. Determinant of B transpose is also equals to 2. Because transpose is just switching the one, the columns and the rows. So they will be equals to 2. So basically, this will lead us to this theorem here, 2.3, whereby if A and B are n by n matrices, then determinant of A transpose is equals to determinant of A. And the determinant of AB is equals to determinant of A, determinant of B, determinant of A, determinant of Then the last property here, 2.4. If A is invertible n by n matrix, then determinant of A inverse is equals to determinant of A, and then you put inverse outside, which is just similar to i.e. determinant of A inverse is just similar to 1 over what? Determinant of A, 1 over determinant of A. 1 over determinant. So we can prove this one, so simple. So we can take this as if we prove this. So we can take A as an invertible matrix, then A and then A inverse is equals to what? In. A inverse is equals to In. Now, if you introduce the determinant, then determinant of A inverse is also equals to determinant of In. Determinant of In. And determinant of In is just what? What? It's just one. Then using this property here, property 2.3, then we can just say determinant of A, determinant of A inverse equals to what? Equals to 1. So therefore, we can divide everywhere here by determinant of A. So then determinant of A inverse is equals to what? 1 over determinant of A. So I'll give you, in your exam, I'll give you one example and I'll ask you most of these things here. So I'll ask you to get the determinant of A inverse, determinant of the first one, the remark that I gave you. So it looks like 3, and then, so determinant of 3, what is the determinant of 3A or something, 3A or something like that, and then all this. So expect this one in your third exam. Any question up to that? Right, now let's come to the next section, which is section 3.3. We'll just be doing here the Cramer's rule. 0.3. Rule. So in this 3.3, there is Cramer's rule. There is a volume and linear transformation. So what we will just do is the Cramer's rule. So this is another way of solving the linear equation, of solving a linear equation. Okay, let's start with 1.1. And what is a Cramer's? What is this Cramer's rule? Cramer's rule. Now, if we let A to be equals to the vectors A1 all the way to, let's say, AN, okay, be n invertible, n by n matrix, and B be element of R of the vector space Rn. Now define AJB to be equals to the vector A1 all the way to AJ minus 1, and then we replace AJ by our B, and then we continue like that, AJ plus 1, and then after that, the last one, which is AN. Okay. So AJB, where there is the vector AJ, then we replace by the constant terms, which is B. When it is AJ plus 1 here, we replace this one by what? AJ plus 1, or the last one, the AN, then we replace the last one, AN, by what? Okay, I'll show you that. For J to be equals to 1, 2, all the way to N, all the way to N. The matrix equation AX equals to B, where X equals to X1 all the way to Xn, has a unique solution given by, so we get a unique solution, which we get this one by the solution of Xj to be equals to determinant of AJ B all over determinant of A, all over determinant of A. Now, if we have this, so this is actually a matrix equation, which we get from the linear equations. Now, if you want to get a solution of, let's say, x1, so it's x1 here, determinant of A1 B, whereby the vector A1 we replace it by B, and then we name the other ones, and then we find the determinant. All over the determinant of A. All over the determinant of A. Same thing with X2. So X2 will be determinant of A2. That means the vector A2 will be replaced by this constant B. And then we get a determinant all over the determinant of A. So determinant of A is actually constant. So first of all, you get a determinant of A. The only thing that changes here, to get the X1, you replace the column of A1 by B to get X2 later. So you do the same thing. Okay, I want us to prove this because I feel like it's a little bit important to you. So you might find this one somewhere else. So let's prove this one. Let's prove. So we start by, we may assume that n is actually greater or equals to 2. N is greater or equals to 2. So the dimension should be more than 2. Then since A is invertible matrix, then determinant of A is not equals to 0. Determinant of A is not equals to 0. Then the matrix equation AX equals to B has the solution X to be equals to A inverse B. So it has that solution A equals to X equals to A inverse of B. Then this matrix A, we can multiply this A by the standard vectors. Let's say E1 all the way to, let's say, EJ minus 1, and then X EJ plus 1, and then all the way to what? En. Okay. So what do you mean here? So we know that this is just the first one is 1, 0, 0, right? So when you formulate this one and then we replace, when there is J, EJ, then we put it X, okay? X1, X2, up to the last one there. Then it is actually similar to A1, AX. Since these are just the standard vectors. Okay. This is the X. So when you multiply that A, you will remember when you multiply by identity, right? By the identity, a matrix by the identity, you get the same set matrix. And that identity is just actually the standard vectors. Okay. So A dot standard vectors is equals to, for the B one, then it is actually equals to A. So when you open these brackets here, so when you open the brackets, you put A inside A E1 all the way to A EJ minus 1, and then what? AX, right? AX, and then EA EJ plus 1, and then continue like that. A E and A E N. Okay. So this AX here is equals to what? B. So then this is equals to A E1 all the way to A EJ minus 1, and then B A EJ plus 1, and then A E N. Now, this A E1 is just the same as what? The vector. So this is actually the same as A1, right? And then you continue like that. This is what? A J minus 1, and then this is B, and then A J plus 1, all the way to A N. Okay. Now, if you look at these, so now how many vectors are here? How many vectors are actually? How many vectors are remaining here? So after we use this one, we replace this one. So how many of them are remaining? In the last one here, if you put the last one here, so basically what remains there is actually the same as this is equals to A J. So what remains is actually J. And this is just like that. What remains there is AJ. So then if we introduce now the determinant here, then if we put the determinant in both sides here, since this is just A and then all these, then it will just be determinant of A, okay, of this one, and then determinant of E1 all the way to X, and then all the way to En there, equals to determinant of AJ, and then B there, AJ and then B. Okay. Now, since these are just the standard vectors here, then the determinant here will just be determinant of A, and then multiply by what? The vector X, equals to what? Determinant of AJ. And then finally, this is just the same as X, equals to determinant of A, J, and then B, all over determinant of A. And that is how to get a solution. Example number 1. use Cramer's rule to solve the following linear system. Solve the following linear system. Okay, so we have minus 5x1 plus 3x2 equals to 9. 3x1 minus x2 equals to minus 5. Minus 5. So that is now the solution there. So the solution. So we need to write this in matrix equation form. Matrix equation form. Whereby this is the same as what? Minus 5, 3, 3 minus 1. And then this is x1 and what? X2 equals to what? 9 and minus 5. 9 and minus 5. So we write it in. Now, so this is A, this is our X, and this is our Y. Okay. So here, first thing you do is get a determinant of A. And this is just similar to getting the determinant of minus 5, 3, 3, and minus 1. And this is equals to minus 5 minus 9. And this is equals to what? Minus 4. Okay. Right. Okay. The first variable there, x1. So to get x1, then this is similar to getting the determinant of a1, b, all over determinant of what? Determinant of a. Determinant of a. Now, a1b is just, you replace the first row, the first column, sorry, by, okay, so you replace this one by this B to get A1B. So this is the same as 9 minus 5, and then you retain the 1, 3, 1. So that is A1. A1. Now, let's get the determinant of this. So determinant of A1B is equals to determinant of 9 minus 5, 3 minus 1. This is equals to minus 9 plus 15. And this is equals to what? Is it 6? 6. That is equals to 6. So therefore, the x1 is equals to what? Determinant of this, which is 6. All over what? Determinant of A is minus 4. And this is equals to -3 all over 2. All over 2. Okay, next one. X2 equals to determinant of A2B. All over determinant of what? Determinant of A. Then A2B is we replace the second column by 9, -5, which is -5 and 3, 9, -5 here. Then determinant of -5, 9, 3 minus 5 is equals to 25 minus what? Minus 27 equals to what? -2. So then x2 equals to -2 all over what? which is equals to 1 over 2. That is the solution. So which of the methods that we have done, which one is the easiest?
Wait, depends
This
on the
one.
matrix. Maybe, yeah.
The matrix is easy. Or it depends on the matrix. Yeah, actually it depends on the matrix. This can be simple if there are 2 by 2.
Yeah.
But if it's a 3 by 3, then you rather use the reduced echelon form, because definitely you will have to reduce to get the determinant.
Yeah.
So you rather do the augmented matrix and then you reduce it completely.
Mhm.
Yeah. So this is actually so easy for the 2 by 2 matrix. Okay. Another example. This one I might give you in your exam. Actually give you this one in your exam, but I will just be combining just like the first exam, whereby I was asking for the Cramer's rule. We are just getting the unique solution. We're just getting the unique solution. Okay, example number 2. Determine all possible values of the parameter S such that the following linear system has a unique solution and describe the solution in this case. So we have the linear system as 3s x1 plus 5x2 equals 3, 9x1 plus 5s x2 equals to 2. So determine all the possible values of s and give us the unique solution. Okay, so we do the same thing. So solution. So we get A, and A are just the coefficient matrix. So 3s, 5, and 9, and then 5s, 5s. So then to get the determinant of A, then this is equals to 15s squared, right? Minus 45, right? And this is basically the same as factoring out 15, and then s squared minus what? Minus 3. Minus 3. Now, to get a unique solution here, first of all, this determinant should not be equal to this. Should not be equal to. Basically, this s should not be equal to what? Plus or minus the root 3. So s for A to be invertible, then s should not be equals to plus or minus the root of 3. Plus or minus the root of 3. So then now we get to get a unique solution, then we need to get a determinant of A1B which is equals to determinant of 3, 2, and then 5s. And this is equals to 15s minus 10 minus 10. And this is basically the same as what? We can factor out 5, and then you get 2s, 3s, minus what? Minus 2. Minus 2. So in this case also, s should not be equals to what? Should not be equals to 2 over what?
3.
2 over 3. Then also get the determinant of a to b, which is the same as 3s 9 and what? 3 2, which we get what? Minus 6s, so 6s minus 21. 27, which is similar to 3 outside, and then 2s minus what? That's 9. Also, s should not be equal to what? 9. Okay, now the matrix equation has unique solution if and only if A has exactly 2 pivot positions, right? If you remember that. Then also has unique solution if A is what? Invertible. A should be invertible, so it should not be equal to 0. And then also has unique solution if determinant of A is not equal to 0. Also this one, 15 s squared minus 3 should not be equal to 0. In this case, s should not be equal to what? Plus or minus the root of 3. Plus or minus the root of 3. So therefore, the solution there, x1, equals to 5, 3s minus 2, all over what? 15 s squared minus 3, and x2 equals to 3, 2s minus 9, all over 15 s squared minus 3. So those are the solutions. Those are the unique solutions. And that is the end of Cramer's rule. Okay, now let's come to the next section, and this is the adjoint matrix. The adjoint 2 adjoint matrix and inverse matrix formula. Inverse matrix formula. Okay, let's start with adjoint. What is an adjoint matrix? Now, we always use the assumption that n is greater or equals to what? N is greater or equals to 2. Then the adjoint matrix of n by n matrix, let's say A, is adjoint of A equals to, we actually use the cofactors. And these cofactors, you remember the cofactors that you are getting. So you're getting C11, C12, C13. So you use the one. If we are deleting the first row and actually the first row, and then we continue like that as we delete the second, the first row and the second, this first column and the second, like that. So when we're deleting the first row, then we get C11. When we delete the first row and the second column, C12, right? So C11, C12, C13, like that. Again, when we come to the second row, then we are deleting. So we get C21, right? C22, C23, continuing like that. Now, the adjoint in this case, then you see that C11, C12, C13, then we just do what? We just switch. So we switch. So we actually get the transpose. So we transpose. So the C11, C12, C13 becomes, for the adjoint, becomes the row. C11, C12, and then you continue like that. C1n. C1n. Same thing. So the one which was, so the same thing. So C11, then here it becomes C2, now 2-1. Do the same thing here. C22, and then continue like that, C2n. The same thing happens up to the last one, Cn1, Cn2, until the last one here, Cnn, Cnn. So basically we are switching what we are getting as C11, C12, C13 to become now the columns. Where Cij is the ijth cofactor of A, i.e. Cij, we were getting this one by -1, I plus j, determinant of Aij, determinant of Aij, for I to be equals to 1, 2, all the way to n, and also j to be equals to 1, 2, all the way to n, all the way to n. Example number 3. Let's see an example on how to get the adjoint here. So example number 3. Find the adjoint matrix of A, where A equals to 3, 6, 7, 0, 2, 1, 2, 3, 4, 2, 3, 4. The adjoint. So here we just need to compute the cofactors. The cofactors. Okay, let's start from the first one, solution. Compute the cofactors. So we start by getting C11, which is the same as deleting the first row, first column. So which is actually the same as -1, 1 plus 1, determinant of 2, 1, 3, 4. And this is equals to what? 8 minus 3, which is equals to 5. That is equals to 5. Then we go to the second one, C12. We delete the first row and the second column. Is equals to -1, 1 plus 2, determinant of 0, 1, 2, 4. And here we are getting negative, and then this is 0 minus 2, and this is giving us what? And then C13, delete the first row and the third column, which is -1, 1 plus 3, determinant of 0, 2, and then 2, 3. And this is giving us what? 0 minus 4. C21 equals to -1, 2 plus 1, determinant of 6, 7, 3, and 4. And this is giving us negative there. 24 minus 21 is equals to 3. And we are on a negative outside, so -3. C22 equals to -1, 2 plus 2, determinant of 3, 7, 2, and 4. And this is giving us what? Positive there, 12 minus 14, and this is -2. C23 equals to -1, 2 plus 3, determinant of 3, 6, 2, 3. 2 plus 3 is 5, negative there. 9 minus 12 is what? Finally, this is what? 3. That is 3. Then the last row there, C31 equals to -1, 3 plus 1, determinant of 6, 7, 2, 1. And this is giving us positive there. 6 minus 14 is what? 8, and that is what? Negative. And then C32 equals to -1, 3 plus 2, determinant of 3, 7, 0, 1. And this is giving us what? -3 minus 0 is what? -3. And then finally, C33 equals to -1, 3 plus 3, determinant of 3, 6, 0, 2. And this is giving us what? 6. It's giving us 6. So basically, the adjoint, adjoint of A is equals to what? We do what? We take this one as what? The first column. So 5, 2, and then -4. This one is the second column. -3, -2, 3, and this is the third column. -8, -3, and 6.
Way too many steps. It's not that hard.
The only thing that you might confuse,
Mess up.
the only thing that you might confuse is taking this one
As a column.
as a column.
Yeah.
That's why we labeled C though.
Yeah.
Mhm.
Mhm.
That makes sense.
And that is how to get the adjoint. Now, to get the inverse here of the matrix, which you can take this one as 2.2, Then the inverse matrix formula is basically if A is inverted n by n matrix, then A inverse is basically 1 over determinant of A adjoint A. So A inverse is basically 1 over determinant of A. So to get the inverse here, then we basically need to look for the determinant of A, the 1, and then we say 1 over determinant of A, and then this adjoint here, and that will give us the inverse. To give us the inverse. Any question up to there? So we still have 4 minutes. So to get the inverse here, then in this example here, so find, so we can use this one as example for find A inverse in example 3. Or from example 3. So basically we need to get the determinant of A, and the determinant of A. The determinant of A also is easy because we already have the what? The cofactors. We already have the cofactors. So we can use the first cofactors. So we can just say we multiply. We can use the first one, this column here, the one which has as many zeros as possible. Or we can just use this. So we can just take 2C to 2, right? Plus 1. And then C what? 2, 3. And this is basically equals to what? Minus 1. So then A inverse is equals to 1 all over minus 1. 5 minus 3 minus 8. 2 minus 2 minus 3 minus 4, 3, and 6. So the only thing that changes here is just the what? The negatives. So you just put the negative inside. So this is negative 1 here. So that is that is the end of section 2, 3.3. We will meet tomorrow. Tomorrow we will do something small, and then we just review what you might find in your second exam.
Practice.
Yeah, I already put it.
Very cool.
last. Yeah.